This begins by looking at a picture here. Marie and Pierre Curie were the first to purify radium in significant quantities. Radium's intense radioactivity made possible the experiments that led to the modern planetary model of the atom, in which electrons orbit a nucleus made of protons and neutrons. The nucleus, beginning chapter 2. 2.1 Radioactivity. Becquerel's discovery of radioactivity. How did physicists figure out that the raisin cookie model was incorrect, and that the atom's positive charge was concentrated in a tiny central nucleus? The story begins with the discovery of radioactivity by French chemist Becquerel. Up until radioactivity was discovered, all the processes of nature were thought to be based on chemical reactions, which were rearrangements of combinations of atoms. Atoms exert forces on each other when they are close together, so sticking or unsticking them would either release or stop or store potential energy. That energy could be converted to and from other forms, as when a plant uses the energy in sunlight to make sugars and carbohydrates, or when a small child eats sugar, releasing the energy in the form of kinetic energy. Becquerel discovered a process that seemed to release energy from an unknown new source that was not chemical. Becquerel, whose father and grandfather had also been physicists, spent the first 20 years of his professional life as a successful civil engineer, teaching physics only on a part-time basis. He was awarded the chair of physics at the Musée d'Histoire Naturelle de Paris, after the death of his father, who had previously occupied it. Having now a significant amount of time to devote to physics, he began studying the interaction of light and matter. He became interested in the phenomenon of phosphorescence, in which a substance absorbs energy from light, then releases the energy via a glow that only gradually goes away. One of the substances he investigated was uranium compound, the salt UKSO. One day in 1896, cloudy weather interfered with his plan to expose this substance to sunlight in order to observe its fluorescence. He stuck it in a drawer, coincidentally on top of a blank photographic plate, the old-fashioned glass-backed counterpart of the modern plastic roll of film. The plate had been carefully wrapped, but several days later, when Becquerel checked it in the darkroom before using it, he found that it was ruined, as if it had been completely exposed to light. History provides many examples of scientific discoveries that occurred in this way. An alert and inquisitive mind decides to investigate a phenomenon that most people would not have worried about explaining. He first determined by further experiments that the effect was produced by the uranium salt, despite a thick wrapping of paper around the plate that blocked out all light. He tried a variety of compounds and found that it was the uranium that did it. The effect was produced by a uranium compound, but not by any compound that didn't include uranium atoms. The effect could be at least partially blocked by a sufficient thickness of metal, and he was able to produce silhouettes of coins by interposing them between the uranium and the plate. This indicated that the effect traveled in a straight line, so that it must have been some kind of ray rather than, for example, the seepage of chemicals through the paper. He used the word radiations, since the effect radiated out from the uranium salt. At this point, Becquerel still believed that the uranium atoms were absorbing energy from light and then gradually releasing the energy in the form of mysterious rays, and this was how he presented it in his first published lecture describing his experiments. Interesting, but not earth-shattering. But he then tried to determine how long it took for the uranium to use up all the energy that had supposedly been stored in it by light, and he found that it never seemed to become inactive, no matter how long he waited. Not only that, but a sample that had been exposed to intense sunlight for a whole afternoon was no more or less effective than a sample that had been kept inside. Was this a violation of conservation of energy? If the energy didn't come from exposure to light, where did it come from? Three kinds of radiations. Unable to determine the source of the energy directly, turn-of-the-century physicists instead studied the behavior of the radiations once they had been emitted. Becquerel had already shown that the radioactivity could penetrate through cloth and paper, so the first obvious thing to do was to investigate in more detail what thickness of material the radioactivity could get through. They soon learned that a certain fraction of the radioactivity's intensity would be eliminated by even a few inches of air, but the remainder was not eliminated by passing through more air. Apparently then, the radioactivity was a mixture of more than one type, of which one was blocked by air. They then found that the part that could penetrate air, a further fraction, could be eliminated by a piece of paper, or a very thin metal foil. What was left after that, however, was a third, extremely penetrating type, some of whose intensity would still remain even after passing through a brick wall. They decided that this showed there were three types of radioactivity, and without having the faintest idea of what they really were, they made up names for them. The least penetrating type was arbitrarily labeled alpha, the first letter of the Greek alphabet, and so on through beta and finally gamma for the most penetrating type. Radium, a more intense source of radioactivity. The measuring devices used to detect radioactivity were crude. Photographic plates, or even human eyeballs. Radioactivity makes flashes of light in the jelly-like fluid inside the eye, which can be seen by the eyeball's owner if it is otherwise very dark. Because the ways of detecting radioactivity were so crude and insensitive, further progress was hindered by the fact that the amount of radioactivity emitted by uranium was not really very great. The vital contribution of physicist-chemist Marie Curie and her husband Pierre was to discover the element radium and to purify and isolate significant quantities of it. Radium emits about 1,000,000 times more radioactivity per unit mass than uranium, making it possible to do the experiments that were needed to learn the true nature of radioactivity. The dangers of radioactivity to human health were then unknown, and Marie died of leukemia 30 years later. Pierre was run over and killed by a horse cart. Tracking down the nature of alphas, betas, and gammas. As radium was becoming available, an apprentice scientist named Ernest Rutherford arrived in England from his native New Zealand and began studying radioactivity at the Cavendish Laboratory. The young colonial's first success was to measure the mass-to-charge ratio of beta rays. The technique was essentially the same as the one Thomas had used to measure the mass-to-charge ratio of cathode rays by measuring their deflections in electric and magnetic fields. The only difference was that instead of the cathode of a vacuum tube, a nugget of radium was used to supply the beta rays. Not only was the technique the same, but so was the result. Beta rays had the same M to Q, as a mass to, Q ratio as cathode rays, which suggested they were one and the same. Nowadays, it would make sense simply to use the term electron and avoid the archaic cathode ray and beta particle. But the old labels are still widely used, and it is unfortunately necessary for physics students to memorize all the three names for the same thing. At first, it seemed that neither alphas or gammas could be deflected in electric or magnetic fields, making it appear that neither was electrically charged. But soon Rutherford obtained a much more powerful magnet, and was able to use it to deflect the alphas, but not the gammas. The alphas had a much larger value, m to q, than the betas, about 4,000 times greater, which was why they had been so hard to deflect. Gammas are uncharged, and were later found to be a form of light. The m to q ratio of alpha particles turned out to be the same as those of two different types of ions. Helium, a helium atom with two missing electrons, He type of ion, and H2, two hydrogen atoms bonded into a molecule with one electron missing. So it seemed likely that they were one or the other of those. The diagram shows a simplified version of Rutherford's ingenious experiment, proving that they were helium ions. The gaseous element radon, an alpha emitter, was introduced into one half of the double glass chamber. The glass wall dividing the chamber was made extremely thin, so that some of the rapidly moving alpha particles were able to penetrate it. The other chamber, which was initially evacuated, gradually began to accumulate a population of alpha particles, which would quickly pick up electrons from their surroundings and become electrically neutral. Rutherford then determined that it was helium gas that had appeared in the second chamber. Thus, alpha particles were proved to be that type of helium ion. The nucleus was yet to be discovered, but in modern terms he would describe a helium ion as the nucleus of a helium atom. To summarize, here are the three types of radiation emitted by radioactive elements, and their descriptions in modern terms. Alpha particle, beta particle, gamma ray. And then you've got a discussion question. I'll read that in here. Most sources of radioactivity emit alphas, betas, and gammas, not just one of the three. In the radon experiment, how did Rutherford know that he was studying the alphas?